Dr. Ranjani Parthasarathi is a professor in the Department of Information Science and Technology, Anna University. Her area of specialization is computer architecture and networks. One of her special interests is Indian language technology systems. She is actively involved in research in all the areas and has over 50 publications to her credit. She has about 25 years of experience covering both industry and academics.
Welcome to the UGC lecture series in computer science. This is a series of lectures on computer architecture. We have been looking at basics of computers, architecture, instructions, instruction sets and so on. Today we will be looking at some details of some functional units. So, to review the topics that we have covered so far, we have looked at basic operational concepts, understanding of instructions, we looked at types of instructions, arithmetic, logic, data transfer, control, I/O and so on. We have also looked at addressing modes and some details of the instruction sets. So, what we next need to do, the next topic that we will be looking at will be in terms of arithmetic unit. So, remember that we have always talked about 4 basic units that we have, the control unit, the input unit, the output unit and the arithmetic memory unit, and the arithmetic unit comes as a major part within the control unit. So, we need to understand how the arithmetic unit functions. When we look at arithmetic unit, we have basically operations on integers and on floating point numbers that we need to understand how these things actually take place. So, if you look at operations on integers, simple operations, we need to understand our addition, subtraction, multiplication and division, and when we look at it, we also need to understand how we deal with overflow. Similarly, we need to understand how floating point numbers are represented and how the operations are done on them. So, what we will be looking at today will be addition. So, with respect to adders, there are a variety of adders that have evolved over time, and so all of them start with understanding how a simple 1-bit adder works. So, we start with the half adder, which you are probably already familiar with, and then we will look at the full adder, and then we will look at how n-bit adders are constructed using these full adders. So, we will look at 3 different adders in that. We will look at the serial adder, and then we will look at the ripple carry adder, and then the carry look ahead adder. So, let us start with the half adder. Half adder, as you all know, it has 2 inputs x and y, and it produces an output sum and a carry c. So, this is very simple. Input of 0 and 0 gives you a sum of 0 and a carry is 0. 0 1 gives you sum 1, carry 0. 1 and 0 again sum 1, carry 0. If you have 1 and 1, you get sum as 0 and carry as 1. So, this is something that we are all familiar with. So, this is the basis for our entire addition process. So, now if you look at what goes into each of these into coming up with the sum and carry as such, you can see that from this figure that the sum value is just an XOR of the x and y combination. 0 1 1 0 gives you an s. Similarly, the carry is just an AND of the x and y. So, the circuit that we have for the half adder basically is like this. So, you will have an exclusive OR gate to generate the sum and an AND gate to generate the carry. So, you can just see the half adder in action over here. So, you give different inputs and this is the output that you get, both in terms of the sum and the carry. So, if you have a 1 1 as the input to the half adder, you will have a value of 0 for the sum and 1 for the carry. So, now coming to the full adder. Now, what is the difference between the half adder and the full adder? Now, we know that a half adder just takes 2 1-bit numbers and produces a sum and a carry. But when you are actually doing any addition, remember that we may also have to add a carry which comes from a previous position. So, then we look at a full adder, which not only takes the 2 numbers to be added, but also takes into account the carry which is coming in from the next digit, okay, which needs to be taken to the left side digit. So, we are now looking at a full adder which has the 2 numbers which need to be added along with the carry which is generated from the previous position. So, now a full adder therefore will add x, y and the carry, and again it also generates 2 outputs, one is the sum and the next is the carry. So, we differentiate between the incoming carry and the outgoing carry as carry in and carry out. Typically, we use C in and C out to represent these two. So, if you look at the truth table of a full adder, you can see that we have different values of x and y 0, 0, 0, 1, 1, 0 and 1, 1 for different values of the carry in. C in can be 0 or 1. So, 0, 0 and carry in is 0, your outputs are all 0 and 0. 0, 0, 1 will give you a sum of 1 and a carry out of 0. Same thing is true for 0, 1 and 0. If you have 0, 1, 1, you will have a carry out of 1 and some value will be 0. Remember, this is just binary addition. So 1 0 0 again will give you a sum of 1 and a carry out of 0 and so on. So if you have 1 1 1, it will give you a carry out of 1 and a sum of 1. All the other cases you will either have the sum or the carry as 1. So this is the basic truth table that we have for the full adder. Now if you look at the circuit that you have for the full adder, if you look at from the truth table, if you derive the functions for the sum and the carry, they will be as follows. The sum will basically be an exclusive OR of the x, y and the Cn bits, and C out you will see is the combination of these AND functions x y plus y into Cn plus x in Cn. So you can see that pretty much from here. So you will have 0 1 1 1 1 1 resulting in a 1 here, and then 1 0 1 and 1 1 0. So when you simplify this, it will simplify to this function that C out will be x y plus y Cn plus x Cn. Sum will be x exclusive OR with y exclusive OR with Cn. So we need therefore the gates that we need to arrive at these outputs would be, you need an exclusive OR gate, either you can look at a 3 input exclusive OR or 2 bit exclusive ORs combined together to give your S, and the C out would come from this gates over here. So combinational gates we will require will be 3 AND gates and 1 OR gate. So 3 2 input OR gates and 1 3 input OR gate. So this is what our full adder circuit will look like. So a full adder circuit, as you can see, will given the inputs of 1 1 and 1 will give you output both as 1 and 1. Now this is basically what we looked at in terms of 1 bit adders. Now obviously we are not happy with 1 bit adders, we need n bit adders. Now if I need n bit adders, how do I construct these n bit adders using these simple full adders? That is what we need to understand. There are different ways of doing it. One of the simplest ways of doing it is a serial adder, what we call as a bit serial adder. So let us look at what we have in a bit serial adder. So what I am doing here is I have one full adder, right, just one full adder which will keep doing the addition function. Only thing I will keep feeding to this full adder the different bits that are to be added. So for instance, let us say I have an 4 bit number in the x register and a 4 bit number in the y register. Okay, so what I will first do is I will take the least significant bits, feed them as inputs to this. Now this full adder will add these two numbers. Let us assume that initially all these values have been set to 0. So the Ci value will be 0. So when I am adding the least significant bit positions, I am taking the x0 here, y0 coming in from here, C0 let me assume is 0. So these two will get added and that will generate a sum for me, and it will also generate a carry output. The sum output will be S0, which will be stored again in a shift register here, and the carry that I have here I will store it in a flip flop. The reason I am storing it in a flip flop is because next time when I add the next 2 digits from here, next 2 bits from here, this carry needs to be added along with those 2 bits. So now my first step would just be feeding these inputs here, adding it up, storing the sum in the shift register, in the S shift register, and storing the carry in this carry flip flop. Next step will be that I will now shift both these registers. So which means the bits in the second position now would have moved to the first position here, right, and that, so your x1 and y1 would now be inputs to this along with the carry that was stored from the previous step. So the C1 carry that was there in the previous step now comes as input to this. So now remember what our full adder does, it will add your xi, yi and the ci and produce again now your S1 and C2. So the C2 again will be stored in the flip flop. Now when I do the shift operation, I not only shift these two values of x and y, I will also be shifting the S, so that now I have a blank position where this new sum that is generated can be stored. So after 4 such shift operations, you can see what will happen. So at a first shifted out x0, y0 here, I got my S0. Next I have shifted x1, y1, got my S1. Next is x2, y2, you get S2. Next you will do x3, y3 and you will get your S3. So your 4 output bits S would be here, and the remaining carry that you would be generated would be available in this carry flip flop. Okay, so this is a simple adder which is constructed using just one single full adder. But remember, look at the additional circuitry we need to have one additional carry flip flop, and then we need to, of course, we need the 2 registers here, they need to be shift registers, that is registers with a shift capability. Okay, this is one way of doing the addition. But you can see that this is a kind of a slow process, because you can look at each of these operations taking place in one clock cycle. So if I want to add 4 bit numbers, 2 4 bit numbers, I will require 4 clock cycles for this operation to take place. Okay. So if I am looking at adding n bit numbers or 64 bit numbers, this will require 64 clock cycles for this addition to take place. Now that is generally slow. So let us look at how we can kind of speed this up at least a little further. Okay. So another way of doing the addition is using what we call as a series of full adders. We have what is called as the ripple carry adder here. So now look at what we have here. Now we are talking about, again, the example shown here is for a 32 bit adder. Okay. So, I now use 32 full adders. Now, each full adder is responsible for adding each bit position. So, now what I have here is the first full adder will have x naught, y naught and c naught as the input, right, and then the next full adder will have x1, y1 and c1 as the input. There is a carry generated from this stage will go as the input to the carry in of the next stage. So, the carry out of this full adder becomes the carry in for this full adder, and you continue like this with this kind of a connection between the carries of the two of the various full adders. You can go all the way up to the last full adder, where the C31 coming in from here would go as the input to this full adder, x31, y31, c31 would get added, and you will be able to produce the final C out over here. Okay. So, essentially we will get your complete sum over here, S0, S1, all the S bits will produce the sum bits along with the C out, which can be treated as the most significant bit of your sum, or it can be treated as the carry if you are looking at the whole number as a 32 bit number, that is to be the output. Okay. So, this is another way in which we can build a complete n bit adder using these kind of full adders. But look at the complexity here, there we just had when we are doing a serial adder we just had one full adder, whereas now we are using a number of full adders here. Okay. More hardware is required, that is one of the complexities of this kind of an adder. Okay. So, you can just take a look at what happens when we have a 4 bit ripple carry adder, just an example to see how this works. So, let us say the numbers we are adding are 0 1 0 1, that is the first number, and the next number is 0 1 1 1. Okay. Let me assume that initial carry position will be 0, because there is no other carry just generated from any other stage before this, right. So, the first stage the carry in is 0. So, these two numbers, now these are the 3 numbers that will get added, produce a sum of 0 and a carry of 1. Now, this carry propagates to the next stage, and then now these two bits and this carry get added, you produce the carry and the sum, and again that carry will propagate to the next stage. So, you have 1 1 1 as the inputs here, producing an output of 1 and 1. Again that carry will propagate to the next stage. So, you will get 0 0 1 here, giving you an output sum of 1 and a carry of 0. So, this is basically how this will go on. So, what we basically need to see here is that there is a propagation of the carry that takes place. So, that is from one full adder we need to get the output of one full adder for the next full adder's operation to be complete, because remember the full adder requires a carry in to come, and this carry in has to come from the carry out of the previous full adder. So, now what happens therefore is, until this operation gets completed, this operation cannot be completed, right. So, I need to have this output over here before this operation can begin to give me the exact value. Okay. So, there is a delay that is introduced here also, you can see, which is because of the propagation of the carry from one stage to another stage. Okay. This is what we have in a 4 bit ripple carry adder. We will look at how to address this delay that we have a little later, but right now you understand that this is a simple adder that is constructed with n number of full adders. Okay. Now, you can extend this further. So, now we said a 4 bit adder can be constructed like this, a 32 bit adder can be constructed like this, and so on. Now, if I have such 4 bit adders, I can also use it to construct larger adders. So, for instance, I am looking at doing a k n bit adder. Okay. That is, I am talking about n bit numbers that I have k such n bit numbers. Now, these k n bit numbers can then be added by cascading such k n bit numbers. So, what am I talking about over here? So, now look at this whole thing is one n bit adder for me, this is another n bit adder, and so on, and so let's say this is my kth n bit adder. Okay. So, I have altogether k such adders that are available. Now, each adder is going to add 2 n bit numbers. Okay. Similarly, this also adds 2 n bit numbers. So, I am looking at whatever I just shown you this, right, this whole block we are treating as one single block over here. So, when I say n bit adder, it is that entire thing put together. So, this entire thing put together now becomes one block, right. So, I give the C naught as input to this. Now, the output coming out of this entire n bit adder will be my Cn. Now, this will go as the C in input for this n bit adder. Okay. This is, you can look at this as first digit, second digit, third digit, and so on. So, if one digit requires n bits to be represented, so I am talking about now k such digits being represented. Okay. So, each digit is handled by means of an n bit adder that we have here. Okay. So, you can see what we are able to achieve by doing this kind of a cascading of these adders. So, by cascading these adders, you can now construct larger and larger adders. So, that is the advantage we get with this kind of a circuit design. Here what we are seeing here is the carries, they ripple or propagate through blocks. I should tell you why we call this as a ripple carry adder. The reason why we call it as a ripple carry adder basically is that you can see that the carry is the one that has to, you can see that the carry basically is influenced by the carry in coming in the very first stage. So, from here the carry has to ripple through to all the blocks, and then it is only then after it has rippled through all the blocks that you actually get the final output. So, the final output is determined only after the carry has rippled through all the blocks. We normally refer to as a ripple through, or basically what it is doing, it is propagating through all the blocks. That bit which is there, that signal has to propagate right up to the end. Okay. And when we talk of blocks like this being put together, we refer to it as a blocked ripple carry adder. Okay. So, this is what we get with a simple addition kind of a circuit. We will just take a break now, come back and continue with adders and subtractors. Welcome back after the break. So, we were just looking at how n-bit adders are constructed. Now, we will see how the same circuit can actually be used for doing a subtraction as well. So, let us look at what we need to do here. So, let us see, this is our n-bit adder that we had, right. So, with all our x's and y's inputs. Now, to convert this into a subtractor, all we need to remember is, remember a minus b if I want to do, I just need to take the 2's complement of b and add it to a. That means that a subtraction actually is converted into an addition. So, extending that idea here, so let us look at this. I want to subtract y from x. So, what I need to do therefore is take the 2's complement of y and add it to x. Now, what is 2's complement of a number? It is the 1's complement plus a 1. Okay. So, 1's complement you can see is just obtained by inverting each individual bits, right. So, if I have bits here y1, y2, y3 etc. up to yn, okay. So, I have to invert these bits. So, if I say the complement of this y1 bar, y2 bar, y3 bar and yn bar, these become the inverted values of the y's, and I also need to add a 1 to it, remember. Now, that 1 I will add by feeding it through this carry input that I have over here. Now, remember when I am doing normal addition, my first bit C0 is always set to 0 because there is no carry coming in from any previous stage. So, now but when I do subtraction, what I do is I use the C0 to feed a 1 into it, right, and when I feed a 1 into the C0 and I also invert the y inputs over here, I essentially get the 2's complement of this number y. Okay. So, what we do therefore is, of course, we need an inverter here to convert these things into their complements. So, once you have the complements over here and you are able to feed in a y here, the same full adder circuitry that we had for doing addition now can be converted for doing a subtraction operation. So, look at what is happening here. So, all I do is just given the same inputs, invert these, feed in a 1 through this C0 and just do the addition. The output that you have will be the subtraction of y from x. Okay. This is how we use the same circuitry for addition for doing subtraction as well. So, just an example to show how that is done. I am looking at subtracting 0 1 1 0 from the number 0 1 0 1. Okay. So, what is it that I will have here? Look at this. This is again remember this is a full adder, right. So, what I have is 1 0 will be complemented and then 1 is the input that I am giving here. Remember C0 is set to 1. So, complement of 0 is 1. So, I have 1 1 1 as the input to the full adder, giving me 1 as the sum value and 1 as the carry value. So, now these 3 will get added, right. This is 0 0 and 1 getting added. So, I get a sum of 1 carry of 0. Similarly, 1 0 0 getting added, sum of 1 carry of 0, 0 1 0 getting added, sum of 1 and a carry of 0. Okay. So, 1 1 1 1 would be the answer that I would have got. You can look at it as a signed number that is being added. So, because when I did the subtraction, I have converted this number into its 2's complement. So, since we subtracted 0 1 0 1, from that we subtracted 0 1 1 0, the answer will be a negative number, so which is what you will see over here. Now, the two adder and subtractor can therefore now effectively be combined together into a single circuit. Okay. So, what would that look like? All I need is I need to control whether my y input needs to be inverted or not. So, that we do with the help of some kind of an exclusive OR circuitry. Okay. So, you can see what we do here. So, I have one control signal which is called as the add sub control. Now, if it is an addition that needs to do, this add sub control will be set to a value of 0. If it is a subtraction that needs to be done, I will set it to a value of 1. Okay. So, let us see how this will do both addition and subtraction now with the help of this control circuit. So, once I have this control here with a value of 0 given here as the input. Now, when I give 0 as input as one of the inputs to an exclusive OR gate, the output of the exclusive OR gate will just depend on the other input that you have. So, if I have a 0 here, the output will be 0. If it is a 1 here, it will be a 1 here. That is, if one input is 0, it will just pass the other input to the output. which is what I want, right, because I want to do an addition, I just want to have my x's here, I want my y's as input to the direct input to the n bit adder, and I also want my C naught value to be 0. Now, since I said for an addition operation this control signal will be set to 0, this control is what is coming as input over here. So, C naught will be equal to 0, right, and this whole thing now will act as a n bit adder. Now, if I want to do a subtraction, the add sub control will be equal to 1. So, if it is a 1, what will happen to the exclusive OR? One input is a 1. So, if this is a 0, the output will be a 1. If this was a 1, the output will be a 0. So, the exclusive OR gate with one input tied to 1 will basically act as an inverter, which is what we want. If it is a subtraction operation, then the inverted values of y are given as inputs over here, and your C naught also is set to a 1 because C naught is equal to this control function. Okay. So, we are feeding in a value of 1 here, inverting the values here, and then getting the addition done. So, this is a circuit that we can use as an n bit adder subtractor or same ripple carry adder using the n bit adder that we have already seen. So, this is one other simple circuitry that we have. Now, when we do this addition, there is another aspect that we need to remember, which is that we can end up having overflows when we do this kind of an integer addition. So, what do we mean by overflow? Overflow is when the number that is or the result that is generated is out of range. That is, if I have only 4 bits to represent any number, and if my result cannot be represented within those 4 numbers, within those 4 bits, I require 5 bits to represent that number, then I say that an overflow has resulted. Now, what are the cases when you will have overflow operations when you are doing simple integer additions? Okay. So, let us say for instance, this is an example of just 7 plus 6 that is being added. 6 is 0 0 1 1 0, 7 is 0 0 0 1 1 1. Okay. These are the two numbers that are being added here. So, when I add these two, so I get 1 0 1, no carry here, carry is 0, 1 1 0, carry is 1, which will be added to the next stage. So, you will get some output over here, right. So, the final output that is generated is 0 0 1 1 0 1. Now, if I look at this, if I say that the total number of bits that I have to represent my numbers is like 6 numbers over here, 6 bits that I have as shown in this example, then this 1101 can very well be accommodated within these 6 bits. But instead, let us say I had only 3 bits to represent my numbers. Now, my 7 and 6 can be easily represented within a 3 bit number, but when I add the two numbers, you can see that it generates an output of 1101. So, which takes up 4 bits for it to be represented. Or looking at it another way, this is a integer, so it can be a signed integer, right. So, with the sign bit, let me assume this was my sign bit, 0 is my sign bit and 111 is the magnitude. So, 0 is the sign bit, 110 is the magnitude again for the value 6. When I add these two numbers, you can see that the two bits here will have a sign value of 0, whereas when the output is produced, it has a value of 1101. Absolute value of 1101 we can see is 13, but the 1 here represents a sign bit. Therefore, this does not represent the value of 13. In this case, we can say that an overflow would have occurred, because 13 with the sign bit cannot be accommodated within 4 bits. So, when my result is out of range, it cannot be accommodated within the number of bits that I have, then I say that an overflow has occurred. So, when we do an addition, there are only certain cases when an overflow will occur. Whenever I add a positive and a negative operand, no overflow will occur, because the result that is generated will always be within the range. But when I add two positive operands, then it is possible that I have an overflow, or similarly when I add two negative operands, there is a possibility of an overflow. And if I am looking at signed numbers with the most significant bit typically indicating the sign bit, if I add two positive numbers and if I find that the result that I have has a negative value, that is the sign bit happens to be a 1, then I know that it is an overflow. Similarly, true for the other way around, that is if I add two negative numbers where the two numbers will have the sign bit as 1, and if the result that is generated has a value of 0 as a sign bit, then also I know that I have a overflow. Okay, so how do I detect this overflow? Whenever we do additions and if there is an overflow, that needs to be detected, because it means that the result that we got has not been contained within the space that is allocated to it. So, how do we detect overflow? Whatever we looked at just now, okay, that is overflow occurs only when the sign of the two operands is the same, and overflow occurs if the sign of the result is different from the sign of the operands. This is what we saw just now. So, this is what we can use in order to identify that an overflow has occurred. So, if xn minus 1, yn minus 1 and sn minus 1 represent the signs of the operand x, operand y and the result s, then to generate or to detect that an overflow has occurred, I can use this simple equation here. That is xn minus 1, yn minus 1, both these are 1, but sn minus 1 happens to be a 0. So, xn minus 1, yn minus 1 dot sn minus 1 bar, or xn minus 1 bar, yn minus 1 bar and Sn minus 1. That is, these two are zeros, but this happens to be a 1. So, this expression is enough for me to detect an overflow. This can also be rewritten as Cn exclusive odd with Cn minus 1. Okay. So, this is another way in which this can be represented. So, if I have a small circuit therefore, which does this, which implements this particular expression, you can also determine your overflow. So, let us look at the computation of the add time using whatever we have looked at so far. So, we said that this can be a slow process, but we did not really look at how slow this entire process is. So, let us take a look at that now. So, I am computing the add time. Let us take the 0th stage. Okay. The 0th stage has these inputs, right, x naught, y naught and c naught, and produces the output s naught and c1. Now, remember that the carry comes after an AND gate and an OR gate, and the sum is available at if I use a 3 input exclusive OR gate, it is available after 1 gate delay. So, I can say S1 will come after 1 gate delay, whereas the carry 1 is available after 2 gate delays. Okay. So, this is at the 0th stage. So, now look at what will happen when I have 4 such adders. Okay. This is our ripple carry adder, right. So, now S naught we know will be available after 1 gate delay and C1 will be available after 2 gate delays. So, now this second full adder starts its operation only after 2 gate delays, right, because C1 is available only at that time. So, after this 2 gate delays, now S1 will be produced 1 gate delay after that, that is after 3 gate delays from the beginning, and the C2 will be produced 2 gate delays from this. So, here already we had a 2 gate delay. So, 2 plus 2, 4 gate delays before C2 is produced. So, C2 is produced after 4 gate delays. Now, C2 being available only after 4 gate delays, the correct S2 value will be available after 5 gate delays and C3 value will be available after 6 gate delays. So, continuing like that, your S3 will be available after 7 gate delays and C4 will be available after 8 gate delays. So, you can see that for every stage, right, there is a 2 gate delay stage for the carry to ripple through. So, for an n bit adder, therefore, your Sn minus 1, that is the last sum bit that we have, will be available after 2n minus 1 gate delays, and the Cn, the last carry that we have, will be available after 2n gate delays, because remember there is a 2 gate delay for each of the full adders. Okay. So, this is a slow process. So, we need to be aware of the fact that this is a slow process. So, we start looking therefore at mechanisms which can be used to speed up this entire process. Okay. So, what we need to therefore be looking at next is how can this entire process be speeded up, so that without having to wait for so many gate delays, I will be able to do large additions in a very quick manner. Okay. So, we will take a look at that in the next session. We will quickly summarize what we have done so far, how small adders can be built using half adders and full adders. We also looked at how a serial adder can be done, and we looked at parallel adders, we looked at the ripple carry adder. And we also looked at, with respect to the ripple carry adder, how signed addition can also be taken care of, and we also looked at how overflows can be detected. So, these are the things that we have done in today's class. So, a few questions for you to revise the matter covered in today's class. Question number 1, write the truth table for a full adder. Question number 2, what will be the time taken for an n bit serial adder? Question number 3, why is the ripple carry adder considered to be slow? Thank you.